Hi everyone, my name is Gruetter. I'm a PhD student in computer science at MIT, and I will tell you about our project on hardware-software integration. RISC-V rethinks the way instruction set architectures are done. This is also an opportunity to rethink the way we build the components above and below of the RISC-V ISA. It is an opportunity to rethink the way we build complete stacks. Engineering is a social process. At each layer, we typically have a different team of engineers, and at each layer boundary, they have to agree with each other on an interface. Often, these agreements are written down in some interface specification documents, so let's have a look at a few examples. One example is the RISC-V instruction set manual. The nice PDF, which says almost everything about the hardware-software interface. But not quite everything. It deliberately leaves out the platform-specific details, which are then written down in other documents, which might look like this. Here's another example of an interface specification document. It is the documentation of some data structure from the Java standard library. And it is a lot of English text, and I highlighted some text which shows that the implementer guarantees certain things to the user, but also expects certain guarantees from the user. But it's not always the case that everything is written down nicely in an interface specification document. Sometimes you only find out that some value has to be less than or equal to some other value through a bug report. Or sometimes it's not even written down. Sometimes you just have two engineers working on different layers, talking to each other and arguing until they agree on an interface. And in other situations, you can't even talk to another engineer. You're just on your own, looking at some existing code, trying to figure out what could the implementer of this code be expecting from me as the user of this code. So all these different forms is what I mean by interface specification. Now, interface specifications can also have different levels of rigidity. Some of them are implicitly updated daily, while others, such as the RISC-V specification, for instance, have stabilized and stay mostly the same over time. Now, no matter in what form these interface specifications appear, no matter how often they change, and no matter whether the providers of some layer and the users of that layer are the same person, the same team, or not at all, there will always be misunderstandings at these layer boundaries, and there will always be oversights at these layer boundaries. And these then lead to bugs, and even worse, they lead to security vulnerabilities. Now, as an aspiring computer scientist, the question I ask myself here is, can a computer help us solve this problem? And that's exactly our research. To answer this question, we built a prototype system, which is the Internet of Things lightbulb. For this project, we built all the digital parts of the whole stack from scratch, and we're using Bedrock 2, which is a low-level programming language similar to C with verification support. The whole project is very simple at the moment, but we wrote everything with the goal in mind that it should scale to more realistic applications. Here's a picture of our setup. At the bottom left, we have an FPGA on which we put a pipelined processor and a software image, which we both built, and we connected at the top to another dev board, which contains an Ethernet controller and is connected to Ethernet above. And we also connected to a power switch, which has a light bulb attached. And then, if we're using a computer to send a UDP packet containing a 1 into this network card, then our system processes this packet, and it will turn on the light bulb. And then, if we're sending another packet containing a 0, our system will again process this packet and turn off the light bulb. So let's have a look at the interface between this FPGA and the rest of the world. It is a very simple interface. it consists of a set of blue wires going to the Ethernet controller above and of a red wire going to the power switch. What should the expected behavior at this interface be? Well, clearly, we should expect that if a packet containing a 1 is sent, our system should turn on the light bulb, and if we receive a packet containing a 0, the light bulb should go off. But maybe we should also expect more. For instance, if there's some attackers who send malicious data, we should expect that our system does not serve as a gateway to our local private network. And we should also expect that our system cannot be abused to run distributed denial of service attacks against third parties. So here's how we chose to specify all of this. For a moment, imagine that there is a log file which contains one line for each signal which goes through these blue wires and through the red wire. And I will quickly go through this example log file. So the first line might say that we received a packet containing a 1, and that then on the next line it says that we turned on the light bulb. Then it says that we were polling the network card to ask whether there's a new packet available, but none was available. Then maybe we received a packet containing a 0, and then we turned off the light bulb. And then maybe we received an invalid packet, but as you can see in this log, this did not cause us to take any further actions. And then maybe we polled a few more times and did not receive any further packets. Now, in reality, there is no such log file, but we can still use the concept of a log to specify the behavior of our system. And we can do this using a regular expression over the log file. And this regular expression starts with some boot sequence, and then with an expression which is repeated any number of times. And it says that if we receive a packet containing a 0, then we immediately after that, we're going to turn on the light bulb. If we receive a packet containing a 0, the next action will be to turn off the light bulb. And if we receive an invalid packet or no packet at all, we're not going to take any other actions. Note that each of the names appearing in this regular expression is just a placeholder for a more detailed regular expression which describes exactly the bit pattern going through these wires, but I will not present these more detailed regular expressions here. To verify that our system actually satisfies this specification, we're using a tool called coq, that's French for rooster. And coq takes three things as input. It takes the implementation of a system, it takes a specification, and it takes proof instructions. And then it runs for a while and either tells you, yes, the proof instructions form a valid demonstration that the implementation satisfies this specification, or it answers, no, there's something missing here and you have to change something there. coq also comes with an integrated development environment, which allows us to develop the implementation, the specification, and the proof instructions all at the same time in an interactive manner. Using coq, we developed a software image, which is just a list of bytes, and a pipelined processor, and a theorem, which says that if we put this software image at some address, which we chose to be 0, and then set the PC to that address, and then run our processor, then the log of the blue wires and the red wire will respect exactly the regular expression which I presented before. We call this theorem end-to-end theorem because it expresses the high-level behavior of the system in terms of a low-level hardware description language describing the processor. It provides a concise description of the behavior of the whole stack, and it gives us high assurance of the correctness of the system. And this also excludes a large class of security vulnerabilities. Now, if we come back to the picture of the engineers at the different levels of the stack, we can now transcribe all these different interface specification documents into coq files. And then at each layer, we can feed the definition of the upper interface, the implementation of the layer, and the definition of the lower interface into Coq, and Coq will tell us whether this layer conforms to its interfaces. When I say we prove something using Coq, I'm going to give you some flavor of what that means. So I made a little sample proof, and proofs often revolve around invariants on the state of a system. And here I chose a very simple invariant, which says that there's a memory zone containing only addition, subtraction, and multiplication instructions. And then at the end of the zone, there is a jump instruction, which jumps back to the beginning of the memory zone. And we also have a condition requiring that the program counter is divisible by 4 and that the program counter is within a certain range. And then we can state a theorem which says that if a machine satisfies this invariant, then it still satisfies the invariant after running one instruction. And we can prove this by case distinction on the value of the PC. We can say in the first case, it is within this zone between p-inst and the end of this zone. And in the second case, it points to the jump instruction at the bottom. And if we were to forget one case, the Coq proof assistant would tell us. But note that here it cannot be above or below this zone because of the second condition in this invariant. And then in the first case, we do another case distinction over the kind of instruction our PC points to. And for the case of if we get an add instruction, Coq will look up the definition of the add instruction in the RISC-V specification, and it will present us with the updated state of the system after an add instruction, and it will ask us to prove that this invariant still holds for the updated states. And similarly for the other cases, and then using this theorem, we can prove another one, which says that if a RISC-V machine satisfies this invariant, then no matter for how many steps we're running it, it will always satisfy this invariant. Now, this is just a sample proof, and that does not appear as such in our stack, but there is a very similar proof which does appear in our stack, which is the compiler correctness proof. Instead of having a memory zone which only contains add, mul, and sub instructions, we now have a memory zone which contains exactly the instructions emitted by our compiler for a given source program, and we have an invariant which looks like this, and we can prove that this invariant holds. Now, this was about the compiler, but since this is a RISC-V summit, I also want to tell you how we transcribe the RISC-V specification PDF into Coq. Here's a page of the RISC-V specification. It says everything about the corner cases of the division and the remainder instruction. And in Coq, we express this as follows. You can see the names of all the different instructions from the AM extension, and you can see many if-then-else branches which correspond exactly to these special cases. One of the strengths of the RISC-V specification is that it deliberately leaves out certain platform specifics, such as, for instance, the mapping of the physical memory addresses to actual memory or to memory-mapped I/O devices. And this is then specified in a separate document, typically provided by a chip vendor or written by system integrators. And together, these two documents form a complete specification. And we're doing the same thing in Coq. On the left, you can see how we define the load half and the load word instruction. And the definition of the load word instruction contains a placeholder function called load word, which is just a hole for the behavior of what happens when you load a word. And then in another document, you have to fill in the details, such as, for instance, saying which addresses are considered as memory-mapped I/O addresses. And again, together, these two form the complete specification. And in fact, this pattern of parametrizing a specification, we apply it throughout our whole stack. We have parametrized interfaces, we have parametrized implementations, and we also have parametrized proofs. And then we can instantiate these parameters with different values and different behaviors. This is about as much as I wanted to say about our system, and now I want to put it in context with other work. One question people often ask is, can't we just do extensive testing instead of all this proof business? And the difference is that our method can exhaustively verify a system for all possible combinations of parameters and for all possible combinations of inputs and for all possible numbers of steps this system could run. And due to combinatorial explosion, this is not possible with conventional testing, and it will never be possible with conventional testing. Similar to conventional testing, all our proofs run in continuous integration, and whenever you change something, all the proofs are checked again. Now, if this is so great, why isn't everyone doing it? And the answer is really that at the moment, it's a balancing of the engineering efforts. To the left of this balance, I put some bars about the traditional approach, where you spend some time on designing and implementing your system, but then you also spend a lot of time on debugging it and on testing it. On the right, I put some bars for our method, where you probably have to spend some more time on thinking hard about what are the right interfaces. That's the design bar, and therefore, hopefully, the implementation bar might become a bit shorter. And then there's also this proofs bar, where you have to think why your implementation really satisfies this interface. And then there's, at the bottom, there's a very long bar, which is so long that it runs over the slide at the moment. But I believe that there is nothing really fundamental which prevents this bar from becoming negligibly short, so that eventually this right-hand side of the bands will become lighter than the left-hand side. Another question people often ask is whether this has been done before, and yes, it has, but we're not quite satisfied with the way it has been done. A few examples are the CLI Python stack, which is about a 1980s view of a systems stack. There's also the CompCert verified C compiler, on top of which you can put the verified software toolchain, and at the bottom it has an interface which has been extended further down, but as far as I know, people haven't gone all the way down to verified hardware. And there's also the CakeML compiler, which goes from a functional language called ML all the way down to Verilog. In contrast, our project uses Coq, a powerful language for interface specifications. We have a parametrized stack. Since we're using the RISC-V ISA, we can swap out our processor with a commercial RISC-V processor, and our project actually communicates with the external world rather than just writing some result into the memory, which is what other systems do. So to conclude, I just want to say that RISC-V is simple, nice, open, and extensible, and that this is a great match with formal methods, about which I want to point out two things. They enable interface specifications, which are both human-readable and machine-readable, and they can do exhaustive verification of highly parameterized systems. And together, these two form a great match to take software and hardware development to the next level. That's all. Thank you for your attention, and I'm happy to take questions.